Okay, so we've just started with the assumption that V naught is V naught xi plus V naught yj, and that R of 0 is delta y total times j, which coincides with the motion of an ideal projectile that lands at some position delta y total beneath, lower than the position at which it started. With this initial velocity. So using this condition and this condition, and the fact that the acceleration is purely in the y direction, and the magnitude of the acceleration is g, and that the acceleration is downward, we get our acceleration function. We integrate it twice, once to get our velocity function. We get the general velocity function here. We evaluate our constants in terms of the initial condition, and we get this for our velocity function. Then we integrate that once more to get our general position function. We evaluate our integration constants, Cx and Cy, in terms of our initial position, and we get the general position function for this situation. Now, the conditions, the initial condition, for example, R of 0 equals what it equals, depends on the origin of our coordinate system being where it is. If I wanted the origin of the coordinate system to be up here, then R of 0 would be 0. V naught would still be what it is, and we would have vectors from this position. So we'd have a vector out to here, and a vector out to here, and a vector from here to here, vector from here to here finally. And that would be easy enough to set up, but the equations would look somewhat different. For this particular reference point, the origin of our coordinate system being our reference point, these are the conditions we would have. Now we're going to go ahead and apply these to a little more specific situation. Summarizing what we obtained before, for the R of 0 vector equal to delta y total times I, and the initial velocity vector V of 0 equals V naught xi plus V naught yj. Using our general acceleration function, we find the acceleration is negative g times j. Our velocity function, well, you can read it, and our position function. Just the acceleration, velocity, and position functions we just derived. So, let's say we want to solve the problem, what is the position of the projectile at landing? Okay, well, the position at landing at landing, R of, let's call this T sub F, the time at landing, equals what? V0x times T sub F I plus negative 1/2 G T F squared plus V0y times TF plus delta y total times j. In other words, just substituting our TF in for all the t's here. And that has to equal V0x TF times I plus negative delta y total times j. And make sure we've got all that. Maybe aim the camera just a tad bit lower. Okay? And why is that? Well, the landing, wherever it's going to land, your final vector is going to be R of TF. There it is. And since the origin of the coordinate system was placed at the distance delta y total below the axis, and I've just disproven my, I was thinking of the initial position being up here, in which case your R of TF would have a negative delta y total for its j component. But that's not the case. I've just disproved my own assumption here. It's just 0 times j. Now, this has to equal this. V naught x TF is the same in both expressions. We don't know what TF is, but we know that negative 1/2 GTF squared, etc., is going to have to equal 0. So we very easily solve that equation, and we solve that for TF. It's a quadratic equation, not at all difficult to solve. Okay, now again, the j component of R of TF here has to equal the j component of R of TF here, and we know that R of TF is going to equal V0xt times I plus 0j. Setting the two j components equal, we obtain this equation, which is a simple quadratic equation in T. And we can solve that equation very easily using the quadratic formula. It's pointless to try to factor this or complete the square. Maybe not pointless to complete the square, but that's more pain than we want to go through right now. We simply write down what the quadratic formula tells us, and that's straightforward. Just briefly, you're going to have negative the coefficient of TF, which is going to be negative V0y, plus or minus, it's going to be the coefficient of TF squared. That will be like your A, B, and C terms in the quadratic formula. That'll be your B squared, it'll be V0y squared, and then minus 4 times this times this. Well, 4 times this is going to be negative 2 GT, and negative 4 times that's going to give you a plus 2 GT times delta y total. And then that's going to be divided by double the A coefficient, which would be just plain old G, plain old negative G. When we simplify that, we get negative V0y over negative VG, which is V0y over G, plus or minus this expression. Note that the G, I'm going to put it inside the square root sign, so I'm going to have a G squared in here. And that's going to give us V0y over G squared, that's here, and the 2G delta y total over G squared is going to give us a G in the denominator with this numerator. Again, that's all very straightforward algebra. That should give you no trouble, but of course if you have questions, I'll be glad to receive them. Okay, now, and I will answer them. We want to look at this expression and think about it just a little bit. Okay, are the units of this expression consistent with the units we expect to get? Is this equation all dimensionally consistent? Because if it isn't, that means we've made a mistake. If it is, that doesn't guarantee we did it right, but it makes us feel a little more comfortable. Very, very easy to get the wrong coefficient in some of these, and I might have even done that. Pretty sure I got it right, but I won't stake my whatever's left of my reputation on it. Okay, now we got V0y over G. That's going to be in units of, for example, meters per second divided by meters per second squared, which is going to be units of second, which corresponds with the units we expect here. More generally, it's going to be in units of distance over time divided by distance over time squared, which gives us units of time, which will match our units of time that we expect. The square of V0y over G will be in units of time squared. And since we're going to be taking the square root of this, that's exactly what we've got to have for each term of that we see within the square root. Similarly, over here, we'd better get units of time squared. And you can verify that if we divide units of distance by units of distance over time squared, we're going to get units of time squared. So the units are all consistent with what we hope and expect to get. Now there's a little more in this. If we didn't have this term over here, then our square root would be the square root of V0y over G quantity squared, which would just match the V0y over G that we have here. So that for the plus, we would get 2V0y over G. For the minus, we would get just V0y over G because the minus would match this term. The 2 delta y total over g makes this expression a little bigger than v0y over g, so that when we add it, we get something a little bigger than double this, and when we subtract it, we're going to get something a little less than 0. Now you should try to make notes of those comments and convince yourself that what I just said is true. I'm not going to write this out in detail. We're trying to keep this relatively brief. So that's kind of where we are with this solution. So kind of summarizing what I said and taking it just a little further maybe. If delta y total is 0, and that would correspond to projectile that just goes up and comes back to its original level, so that delta y total 0 would mean you started from here and came back to the x-axis. If delta y total is 0, then either TF is 0 or TF equals 2v naught y over g. And what does that mean in common sense terms? It simply means that there are two times at which that projectile would be on the x-axis. One, when it started, which was at TF equals 0, or T equals 0. So that T naught equals TF, and the thing is there at T equals 0. And the other is it goes up and it comes back down, and going up, it's got to lose its v naught y. The rate at which it loses velocity is g, so that to go up, it's going to go up until the time is equal to v naught y over g without the 2, and then it's going to come back in an equal time. And again, you should break that down to common sense. A formal solution is great. It's general. It gives us all kinds of information, but we've got to be able to interpret it. And we should be able to interpret it in the simplest possible terms. Now, if delta y total is not 0, then I say, well, if delta y total is 0, we get this, or else we get what? Well, if delta y total is not 0 and it's positive, of course delta y total could be negative, and you might want to interpret that too. I recommend that you do. But if delta y total is positive, then it follows that the square root, as I said before, is going to be greater than v naught y over g, so that when we subtract it from v naught y over g, we get a negative. So the final time is 0, is less than 0. What's that mean? That means that if we extend this parabola backwards in time until it hits the x-axis, we're going to get a solution. We're going to get a time before we started at which this could well be a projectile that was fired from here, but we don't start tracking it until we get to this point. And we set our time, we start our clock at this point instead of this point. It means the projectile was here that much earlier. Okay, so, and then the projectile moves on to here and gets down to here at another time, which is greater than 2v naught y over g. That means it's greater than the time it takes it to get from here to here, where it goes up to its maximum height, then comes back down. Then you've got an additional time here. Now you can think more about the details of what that's telling you, but there's a complete solution of the projectile problem for these assumptions. And if you make other assumptions, it's just going to change your R of t function. It's not going to change the kind of mathematics you have to do to get a solution.